This particular video episode is going to take a look at something known as photoelectron spectroscopy, which is a means of figuring out the structure of atoms, the electronic arrangement of electrons, by using a concept originally developed by Einstein. Einstein had an idea of something that was known as the photoelectric effect. Essentially, what the photoelectric effect tells us is that if we have some light energy of energy E equals h nu, that the light energy can strike the surface of something like an element. If the energy of the light is sufficient, it can actually cause an electron to be ejected from the surface of the element. Let's take a closer look at a very simplified version of an atom. Just focusing again that the nucleus in an atom is always going to be positive, and the electrons located in the electron cloud are always going to be negative. Because of the positive charge in the protons in the nucleus and the negative charge of the electrons in the electron cloud, there's going to be an attraction between the protons in the nucleus and the negatively charged electrons in the electron clouds. In the photoelectric effect, there's going to be some incident light that strikes the surface of our atom. We can figure the energy of the incident light from E equals h nu. If the incident light is of sufficient energy to cause the attraction between the nucleus and the electron to be broken, then the electron gets ejected from the atom. So to repeat that again, if the incoming light energy is greater than the attractive force between the positive nucleus and negative electron, then the negative electron is ejected from the atom. Now, because the electron that's ejected is moving, the electron possesses kinetic energy, which is 1/2 mv squared. Now, because of the law of conservation of energy, we can figure out the energy that's holding the electron to the nucleus. This energy that holds an electron to the nucleus is sometimes referred to as the binding energy. The total energy in our system comes from the incident light which is striking our atom. We can get that from E equals h nu. That has to be equal to the combination of the binding energy and the kinetic energy of the ejected electron. So our incident light energy, E equals h nu, is equal to the total, the combined energies of the binding energy, which holds the electron to the nucleus, and the energy of an electron as it gets ejected, when it has kinetic energy. Because we can readily measure the frequency of the incoming light, we can determine the energy of the incoming light, and we can measure the velocity of an ejected electron, which allows us to determine the kinetic energy. This then lets us get values for the binding energy, or the energy that holds an electron to the nucleus. The binding energy is sometimes also referred to as the ionization energy, which is the amount of energy necessary to strip an electron off of an atom and turn it into an ion. Photoelectron spectroscopy, or PES, it can be used to identify atoms and also to provide very detailed information about the electronic structure, which is the location of the electrons in an atom. For an example, let's start out and look at the simplest atom, hydrogen. For purposes of our examples and explanation, we're going to be using something known as the shell model of the atom. In our shell model of the hydrogen atom, we see we have one positive proton in the nucleus, and we have a single electron in the single shell indicated in our hydrogen model of the atom. Some light now strikes the surface of our hydrogen. The light has energy E equals h nu. Our single electron from the hydrogen gets ejected. A common way that photoelectron or PES data is displayed is they have a vertical axis with number of electrons, and the horizontal axis has the binding energy to give us our photoelectron spectroscopy spectra, or our data. This would now be our photoelectron spectroscopy data for a hydrogen atom. The height of this peak indicates that we have one electron that got ejected. And then the value of the energy here, 1.31, that's an indication of the amount of energy that was the binding energy for the single electron removed from our hydrogen atom. Now let's take a look at the helium atom to compare to our hydrogen. Now in a helium, we'll notice the nucleus now has 2 protons, and the electron cloud contains not 1 but 2 electrons. Because helium has more positive charge than hydrogen and more negative charge, that means there's going to be a stronger attraction between the nucleus and the electrons in the energy level 1 shell in the helium atom. Because of the greater attraction between the nucleus in helium and its electrons in the energy 1 shell, helium will require more energy to eject an electron from the atom than what we saw in hydrogen. When we now see the photoelectron spectroscopy data for helium, a couple things emerge. One, the peak is twice as high as what we saw in hydrogen, which indicates that there's 2 electrons, not 1 electron. And then the binding energy is 2.37 versus 1.31, which is indicative that these electrons are being held tighter to the nucleus in helium than what we saw in hydrogen, which would be the case because in helium we have the 2 protons instead of just the 1 proton in the nucleus, as is seen in hydrogen. Let's go forward and take a look at the lithium atom using our shell model. A quick peek shows us that lithium now has 3 protons in its nucleus. Continuing with our shell model of lithium, if we look at the inner shell, we have 2 electrons at energy level 1 in our lithium model, and then there's now a new shell which corresponds to energy level 2, and in our lithium that contains a single electron. In our lithium atom, the electrons, we have 2 electrons that are at energy level 1. Those 2 electrons at energy level 1 are pulled in even closer and held tighter in lithium than they were in helium and hydrogen because we now have a charge of +3 in the nucleus. So that's pulling very tightly on the negative charges in the level 1 electrons. Whereas if we look at our n equals 2 electron at the second energy level, this electron is now further away from the nucleus, and because the electron is further from the nucleus, that's going to weaken the attractive force between the nucleus and the electron. When we see the photoelectron spectroscopy for lithium, several things emerge. This first peak is twice as high as the second peak, indicating twice as many electrons. This corresponds to 2 electrons in the inner ring of the core model of lithium. This peak being half as high corresponds to only a single electron, which we saw at the second energy level. We also see, looking at the energy, 6.26 is a fairly high energy for the removal of those electrons, which is indicative of those electrons must be close to the nucleus. If we look at the other electron, we see that the value for the energy is fairly low, 0.52. That's indicative that that electron is further from the nucleus, which is another way of saying it's in an already higher energy state. So it took less energy to remove that electron from the atom. Let's look at an atom with a few more electrons. Let's do one more example and use sodium. As we look at our sodium atom, let's first take note that we have a positive 11 nucleus. That positive 11 nucleus is going to hold those inner electrons at n equals 1 very tightly. So we're going to see a very high binding energy for the 2 electrons located at the first shell in our model. Looking at our model, we also see we have just a single electron at energy level 3 in our third shell in the shell model. Because that's getting far away from the nucleus, the binding energy will be fairly low. As positive and negative charges get further and further apart from one another, the attractive force gets lesser and lesser. So in this case, being all the way out here at energy level 3, that electron is fairly far removed from our nucleus, so the binding energy would be much less for this n equals 3 electron. Now this would be what the photoelectron spectroscopy results look like for a sodium atom. And again, let's take a peek at the information this provides us. We see one piece of data, a very high energy of 104. This corresponds to the two innermost electrons at energy level 1. We also see we have a very low energy of only 0.50. Plus the peak height, if we look at it, is only half as high as what we see for the 104. The 104 energy corresponds to 2 electrons. This peak corresponds to a single electron, which would be the outermost electron at energy level 3, which would require very little energy to remove. We see 2 peaks remaining. The first peak is 2 electrons high, and this is triple the height, which would be indicative it represents 6 electrons. Looking at the energy for each of these, they're not too far apart from one another, 6.84 and 3.67. This is an indication that we have 2 different sets of energy at n equals 2. This corresponds to our 2s electrons and then our slightly higher energy 2p electrons. The peak of 2 electrons is the 2s. This peak with 6 electrons in it would be representing our 2p sublevel at energy level 2. The spectra then is giving us very detailed information about the atom and data to support the concept of S, P, and D sublevels. This 104, corresponds to 1s2. The second peak would be 2s2. This third peak, 3 times as high, would be 2p6. And this peak out here, very low energy, and half the height of our 2 electron peaks is 3s1. So this gives us data to support the S, P, and D sublevel concept of the atom. Let's try one last example going in reverse. If we have some photoelectron spectroscopy data, can we determine the atom represented by this data? To start, we see we have very high energy of 52.6. That represents our 2 inner electrons. This would be 1s2. Our next peak we see, it has the same height as the first one, so that means we also have, therefore it's 2 electrons represented, but we have much less energy. 3.12 compared to 52.6. That's telling us we're in a different shell now for this particular atom. This would be our 2s2 electrons. The last peak we can see it's twice as high, so it represents 4 electrons, and it has less energy, which means the electrons are located at a slightly higher energy state. This would be our p electrons. And with the height being twice as high, it represents 4 electrons, so we have 2p4. This electron configuration and the PES data match with the element oxygen.